Let's first try to understand what an efficient search could look like. Imagine a scenario where Omer and Gino finish watching Across the Spider-Verse on Netflix. Feeling inspired, Omer wanted to recreate a scene 40 minutes into the movie as a painting. They both have a friendly race to find that scene. At a 140-minute runtime, Omer's plan is to rewatch the entire movie from the start and pause at the desired timestamp. Gino, a helpful but busy friend, has a different strategy. He wants to seek into the middle of the timeline and notice the time. If he overshot, he would look to the left half of the timeline, and if he undershot, he would look to the right half of the timeline, and then he would proceed to recalculate the midpoint. He would continue this process of trimming the timeline relative to the midpoint until he finds the timestamp. The benefit of Gino's strategy becomes more pronounced with a longer movie runtime. Let's look at the problem of search more concretely. Provided a set of numbers, our task is to find a particular element. If the numbers aren't sorted, we have no choice but to look through all the elements. We want to be pessimistic in our analysis, so in the worst case, the element may be found all the way at the end of the list. So we say that the algorithm grows linearly with input size n. In other words, a list of size n implies n operations to potentially find the element. What if instead the numbers were sorted in non-decreasing order, like with the movie timeline? Our original approach would still work, but we could also apply Gino's clever strategy, binary search. We set two pointers, L and R, to define the bounds of our search space, which is initially the entire array. The size of this search space can be found by taking the difference of the pointers and adding 1. Meaning, when the pointers meet, we have exactly one element to consider, and when they cross, our search space becomes empty. We apply the following strategy until our search space is empty. We calculate the midpoint of the search space and compare its value against our target key. Consider the case where the midpoint value is less than the target. Remember that the input is sorted, so think about how we can trim the search space to avoid checking redundant elements. In this case, we undershot, so we look at the right half of the search space. This is because all the elements on the left half, including the value of the midpoint, contain elements that are less than the target. Similarly, when the midpoint value is greater than the key, we overshot and we need to look on the left half of the search space. The simplest case is when the element is found, in which case we just return true immediately. If throughout the execution the target is never found, then the bounds would have crossed and we know that the element doesn't exist. Intuitively, this is faster, but exactly how fast? Notice that our search space is halved with each iteration. We could look at this bottom up and notice that it actually doubles starting from 1 up to n. When there's one element remaining, we can definitively tell whether a target exists, so this is treated like a base case. The mathematical function log2 of n answers the question of how many doubling steps are required to reach n, and this gives us the worst case number of executions for some input size. Notice how this algorithm scales much better with larger and larger input. The takeaway is that for every element, if we can partition the remaining elements into those that are less than or equal to it, and those that are greater, we can sharply reduce the search time.